Welcome to this lecture on sampling distributions, specifically focusing on the chi-square distribution probability density function. Imagine you are a quality control inspector and you need a mathematical way to measure accumulated errors. Today, we will build this powerful statistical tool from the ground up, understanding not just its formula, but exactly why it works. Let us begin by imagining a factory making metal rods. You want them to be exactly 10 centimeters long. Sometimes they are too long, sometimes too short. These individual errors often follow a standard normal distribution, which is a classic bell curve. But what if we only care about the magnitude of the error? To remove negative signs and heavily penalize large mistakes, we square each error measurement. When we add up these squared errors from multiple independent samples, the total follows a brand new pattern. This is the chi-square distribution, the ultimate tool for measuring accumulated variance. Now that we understand the intuition, let us look at the formal definition. The chi-square distribution is defined as the probability distribution of the sum of the squares of several independent standard normal random variables. A standard normal variable has a mean of 0 and a variance of 1. If we take a specific number of these variables, square each one and add them together, we get a chi-square random variable. That specific number is called the degrees of freedom. It simply tells us how many independent squared variables we are adding up to get our total. This formal definition leads us directly to the mathematical equation that describes this distribution. This is the probability density function, or PDF. It gives us the shape of the curve, showing which total squared errors are most likely to occur. Let us look at the symbols. The variable x represents the specific value of the total squared error, which must be greater than 0. The letter k represents the degrees of freedom. Finally, the Greek letter gamma represents the gamma function, which is a continuous extension of the factorial function. As the degrees of freedom increase, the exponent changes, drastically altering the shape of the curve. Before we use this formula, let us visualize what it actually looks like. Here we see the chi-square probability density function plotted for different degrees of freedom. The horizontal axis represents the total squared error, and the vertical axis is the probability density. Notice that the curve only exists for positive numbers because the sum of squares cannot be negative. For small degrees of freedom, like the red line, the curve is heavily right-skewed. But as the degrees of freedom increase, look at the dotted purple line. The curve gradually loses its skewness and becomes beautifully symmetric, approaching a classic normal bell curve. Now that we have seen the shape of the curve, let us put the formula into practice with a concrete example. Suppose we are tracking the squared errors of two independent sensors. This means our degrees of freedom is exactly 2. We want to find the exact value of the probability density function when the total squared error is also exactly 2. We start by writing down our general PDF formula. Then we carefully substitute our specific values. We replace every instance of k with 2 and we replace the variable x with 2. This sets up our equation perfectly. Continuing with our calculation, we can now simplify the arithmetic. In the exponents, 2 divided by 2 simplifies to 1. This makes the exponent in the numerator 1 minus 1, which is 0. In the denominator, the input to the gamma function becomes exactly 1. We know that any non-zero number raised to the power of 0 is 1. And the gamma function evaluated at 1 is equal to 0 factorial, which is also 1. Substituting these back, the complex terms disappear. We are left with 1 over 2 times e. This gives a final numerical value of approximately 0.184. Physically, this is the exact height of the probability curve at that specific point. Now that we have successfully used the probability density function, let us understand exactly where it comes from. To derive this PDF, we use a tool called the moment generating function, which acts like a DNA blueprint for a probability distribution. We start by defining a new variable y as the square of a standard normal variable z. The moment generating function is defined as the expected value of e raised to the power of t times y. To compute this expected value, we must integrate the function multiplied by the standard normal PDF from negative infinity to positive infinity. This sets up the foundation for our derivation. Moving forward with our integral, we can simplify the expression by combining the exponents. We factor out the squared z term from the exponential functions. This algebraic simplification is crucial because it allows us to evaluate the complex integral by comparing it to a known normal distribution. By performing a substitution that scales the variance, this entire integral evaluates exactly to a simple algebraic expression, 1 minus 2t all raised to the power of negative 1/2. This beautiful result is the moment generating function for a single squared standard normal variable, representing exactly 1 degree of freedom. Now that we have the blueprint for a single squared variable, we must find it for the entire sum. Let our total chi-square variable be called x, which is the sum of k independent y variables. A beautiful property of moment-generating functions is that the function for a sum of independent variables is simply the product of their individual functions. Since each variable has the exact same blueprint, we multiply it by itself k times. This is mathematically identical to raising it to the power of k. The final expression perfectly matches the blueprint of a specific gamma distribution, which proves that our chi-square PDF must be exactly the gamma PDF we saw earlier. This derivation brings us to the official moment-generating function for the chi-square distribution. This compact formula is the mathematical engine behind the distribution's properties. Let us review the components. The function is denoted by m sub x of t. The variable t is simply a dummy mathematical variable used in the transformation, and it must be strictly less than 1/2 for the math to hold. The letter k, as always, represents the degrees of freedom. If you increase the degrees of freedom, the exponent grows, which fundamentally changes the moments of the distribution, such as its mean and variance. With this moment-generating function in hand, let us use it to find the expected value or mean of the distribution. A powerful rule in statistics states that the first derivative of this function, evaluated at 0, gives the exact mean. We begin by taking the first derivative with respect to the variable t. To do this, we must use the chain rule from calculus. We bring the negative k over 2 exponent down to the front as a multiplier, subtract 1 from the exponent, and then multiply by the derivative of the inside function, which is negative 2. Continuing from our derivative, we can now evaluate it to find the final mean. First, we simplify the expression. The negative signs cancel out to become positive, and the 2 in the numerator cancels perfectly with the 2 in the denominator. This leaves us with a much cleaner derivative function. The final step is to evaluate this derivative exactly at a t value of 0. We substitute 0 into the equation. The term inside the parentheses becomes simply 1, and 1 raised to any power remains 1. Therefore, our final expected value is simply k. The mean of a chi-square distribution is exactly equal to its degrees of freedom. So, we have proven that the mean equals the degrees of freedom. This brings us to how we actually use this in the real world. The chi-square distribution is an absolute cornerstone of modern statistical analysis. Its primary use is in goodness of fit testing, which checks how well observed data matches expected theoretical models. For example, if a casino wants to prove their dice are perfectly fair, they roll them thousands of times and calculate the squared differences between the observed and expected outcomes. This total difference follows our chi-square distribution, allowing them to calculate the exact probability that the dice are rigged. As we wrap up, let us review the most important ideas we have covered today. First, the chi-square distribution models the sum of squared independent standard normal variables, making it perfect for measuring accumulated variance. Second, its probability density function is derived using moment generating functions, taking the shape of a right-skewed curve that becomes symmetric as degrees of freedom increase. Finally, its mean is always exactly equal to its degrees of freedom. You now have the mathematical foundation to perform rigorous variance testing in any scientific field.